Yes, I'm recording this as your teacher, Mr. Stoker. Okay, Newton's Laws is chapter 4. That's the chapter that we spent a lot of time on before this chapter 5, which is sort of like a little extension chapter. We started with the idea that if there's a force, that is a change in motion. I probably should have put that in parentheses, not the acceleration, but oh well. And that change in motion is what we call an acceleration, a speeding up, a slowing down, or a turning. We had to modify this because if you have more than one force, they could cancel each other out. So we modified it to be it's the combination of all the forces. It's the sum of all the forces, or the net force, that actually produces the acceleration. And your book writes that as sigma F. You could write force net if you wanted. It all means the same thing. We then said, though, that's not the whole story, because the object's inertia will also affect its acceleration. So if an object has more inertia, which is mass, measured in kilograms, it will fight against the acceleration more. So the best definition here, the best model for this, is that acceleration is caused by the net force, and it's opposed by the inertia, or the mass. So that ratio, the total force to the total inertia, basically, is the best model for what causes acceleration. Now remember, last chapter, or I should say last unit, we had an equation that described acceleration, like how big it is, but it didn't say anything about what's causing it. So this is describing how big it is, whereas this is describing what is causing it to happen. And the more classic way of writing it is F equals ma, and sometimes that's useful, but conceptually this is the easiest way to keep track of the ideas. We then started drawing force diagrams to help us relate what's the force going on to the, or what's the motion going on to the forces going on. So if the forces are balanced, that means a constant acceleration, or I mean a constant velocity with no acceleration. You could be moving, you could be at rest. If you have more force, say upward or downward, then this thing will accelerate down because there is some leftover force a little bit here in the down direction. So you accelerate down. And this was like an elevator scenario, is kind of how we started. If there is more force in the upward direction, then it will accelerate upward. So those are kind of your three scenarios, like for an elevator. Okay, so the next thing that we looked at here was we sort of then took a look at Newton's laws altogether and said that his first law is inertia. An object in motion wants to stay in motion. One at rest wants to stay at rest. There is this difference between mass and weight that sometimes confuses people. Remember, mass is how much inertia you have. Weight is how much a planet's gravity is pulling down on your mass. So this is a force of gravity. It depends on where you are in the universe, how much weight you have. Whereas your mass is always going to be the same no matter where you are in the universe. You'll always resist accelerating by the same amount. Second law we know. Third law is forces only occur in pairs, or more classically, for every action there's an equal and opposite reaction. Now you might remember we learned that, or went over that first by looking at this video of two carts. One with a bunch of books on it, one that did not have any. And they had these metal hoops on the front. And we said we can gauge the force by how much the hoops compress. So if the hoop on this side compresses the most, it experiences the biggest force. We found that no matter how fast they were moving, and no matter how fast or how big the two objects were, the hoops always compress the same, which is Newton's third law. The force on this cart is always the same as the force on that cart. So the interaction between two objects always produces two forces, and they're the same size but in opposite directions. That's Newton's third law. Now remember, sometimes that gets a little bit tricky considering gravity. If you have like the Earth and the Moon, or anything big and anything a little bit smaller, yes, there's a force of gravity between them, but just because they have the same force, don't expect them to do the same thing. Their accelerations depend on their inertias. So that force on the Earth causes a smaller acceleration, but that same force on something smaller, the moon or whatever, causes a much larger acceleration. We then got into the trickiest stuff of Chapter 4, which is friction. And we said that friction depends on two things. The roughness of the surfaces is the first thing, which is measured by a number between 0 and 1. It has no units. It's a coefficient. Coefficient of static friction or coefficient of kinetic friction. We're using the Greek symbol mu here for that. Kinetic is always a set amount, but static friction can go up to a maximum and then it can't hold anymore, and the object, it's not that it can't hold anymore, the object just is being pushed with a bigger force than it can hold with, and the object breaks free. So this could be smaller than, say, 0.9 or whatever it is for the problem. It could be smaller than that, but that's the maximum it can do. Static friction is always a little bit bigger than kinetic as well. The second thing it depends on is how much those forces or those objects are smashed together, and we measure that with the normal force. Normal force is lowercase n here, not to be confused with uppercase N, which stands for newtons. And when we put those together to find friction, then we're doing mu times the normal force. Now, where these problems got trickier is when you were trying to actually apply Newton's laws. So let's look real quick at a few problems for applying Newton's laws. If you had, say, a fan cart, and you drew a force diagram and said, you know, what's the acceleration of this thing? You could recognize that these two balance and that the push is being eaten into by friction a little bit, or air resistance. So the sum of the forces in the y are 0, but in the x direction, subtract those two to get the net force. The acceleration then would just be that sum of the forces in the x divided by the mass. We had some equilibrium problems where you had to split these into vectors and realize that this force down and that force up would be balanced. You could then take that up force and make a triangle out of this piece right here and find what the hypotenuse was and find what this is. You could then recognize that this side must balance that side and find both tensions. We had problems on an incline where you had to look at cart going down, take the weight straight down, split it into two components. Normal force pushes straight up. The net force is just what's happening down the incline. So it was something like that to find the acceleration. Remember, you can always be forced to use kinematic equations to get to the final answer afterward. Just one quick friction example. I think I've got one here. If I have something being pulled at an angle like a sled, then the upward part of this pull is lessening the normal force, which means friction goes down. So I had to solve for the upward normal force first, then use that to come up with friction after I've done that. There would be the normal force. Find friction, subtract that from the pull in the x direction, then I can find the acceleration from that. Remember, if you're moving at a constant velocity, that means the forces are balanced with friction problems. And that's about all we have time for.